Hey, hello and welcome. In this video, we're going to look at how to calculate power dissipated in R1 through the series circuit here. We know this is a series circuit because there's only one pathway for current to flow. So that identifies series circuit. That also means that we only have one current in this circuit, IT. So knowing that, we can work through how to solve for the power in R1 specifically. So that's going to be the power drop. We can call that P1. So we want to solve for P1. So let's pull out our power law, our triangle here, P, V, and I on bottom there. So from here, we can pick out the fact that power is equal to voltage times current. P equals voltage current. Specifically, we want the power law, right? So we want P1 for the R1 resistor. So we'll call this P1. We'll say that that requires that we get the voltage drop across R1, VR1. And since there's only one current, we know this is going to be IT. So we can pick a couple of paths here. We can solve for both of these, right? We can solve for VR1, solve for IT and use that, or we can plug in what we know Ohm's law can do for this circuit. So let's say we just want to find the total current and we want to break out VR1 here. And so we can draw out our Ohm's law triangle. Say that that is another triangle. We got voltage on top, current and resistance on bottom. And from here, we can say that we want to solve for VR1. So we'll circle voltage and get current times resistance, I times R. And specifically, since we want our VR1 here, then we're going to need to use our R1 resistor and the only current in the circuit, which we know is still IT. So at this point, we can combine the laws. We can say that this is VR1 right, in terms of Ohm's law, and we only have IT left here. So now we can combine these two together, and we'll say that the power law actually says P1 equal to IT multiplied by R1 multiplied by IT. We can reduce this one more time and say that our final equation that we're going to use is P1 is equal to IT squared, because there's two of them there, multiplied by R1. Okay, so now we get to figure out what else do we need, because we don't have everything here, right? We still have, we have R1, we know that, that's 10K here. We can use that right away, but we don't have IT. We need to break down what IT is for us. So we see back on Ohm's law here, if we circle our current, we'll get voltage over resistance. So we can say that our IT is actually equal to voltage divided by resistance. And since we're looking for total, we're going to have to use the total voltage and the total resistance. So we're not going to plug that in directly, but we can solve for that independently. We can say this equals IT, and once we find that, we can plug that into our power law here. We'll do that. So we need to find our RT. We already know VT, right? We know that that is the total voltage in the circuit. And so that means that that's going to be 28 volts. And so we can plug that in. We can say that our IT is equal to 28 volts divided by our RT. And we don't know what that is yet. So let's solve for that. This is a series circuit. So we know that series resistors will sum. So we should find that RT is the sum of our two series components. So we'll write that down. We'll say RT equals 10K ohms plus 32 ohms. And that's going to give us 42 kilo ohms. So 42,000 ohms. So that's what we put on the bottom of our IT equation. Now we can solve out for it. Plug that into our calculator. We can say that we've got 28 volts on top. We'll divide that by 42,000. This one's really, really important. You get all those thousands in there. You can say 42 times 10 to the negative or to the positive 3 because it's a K. Or you can just put in the thousands that you know are there. Let's delete these back out and we'll put in just the thousands that we know. So it's 42,000. Do 3 zeros after that. It gets us the same number. Just make sure you account for all the zeros that you know you have there. That's engineering notation. So at this point, we get total current of 6.67 times 10 to the negative fourth. That's not ideal because negative 4 does not represent engineering notation. Engineering notation has to be in groups of 3. It can be negative 3, negative 6. It can be on the positive side too, positive 3, positive 6. It's in the kilo and mega. But this is really, really small. So we want to make this into a number that we can give a letter to, like in engineering notation. So this right here is our negative 4 spot. We want to move backwards towards our 0 location to get to our negative 3. Right? We can move forward to get to negative 6. and put our decimal point there, but that's going to make it even smaller of a number, a little bit more difficult. So we're going to move it forward 1, put our point there, and get a -3 locations out of it. So our IT is equal to 0 point, that's our -3 spot, 667, so we just moved it forward 1, and now it's times 10 to -3, right? We just moved that decimal point. So instead of writing times 10 to the -3, we can erase that and use our notation and say that it's milliamps. This M represents that -3. Okay, so now we can go back up to our original power equation because we just solved for IT. Now we can plug that in and say that our P1 is equal to, here P1 is equal to our IT squared multiplied by R1. Plug that into our calculator. Say that we have a small little milliamp value. So let's plug in all of those zeros. It's 0.000667. Right? That's our milliamp value. We'll multiply that by our, we'll square it to get our power. And then we'll multiply that by the resistor that we want to know. That is going to be R1. So that's 10,000. 10,000. All of those zeros go in there. Then we get a really small number out, and that's our power. We'll say it's 0.00445 watts. Okay. And we can move that decimal point over. We can go 1, 2, 3 forward here, or backward, yeah, forward. And that would give us 4.45. That's the -3 spot here. So we can give it a milliwatts. That is the power dissipated through the R1 resistor.